This is our second introductory lecture on crystallography. Actually, this lecture is essential for the beginners and just a revision for the students which have already done course on solid state physics. Actually, in this lecture, we are going to see a very simple concept, but that is very essential to study the crystal structure or solid state physics. And this is actually the concept of a unit cell. When you say unit cell, what does it mean? First of all, we will learn about the meaning of this unit cell and how we will construct this unit cell. We will learn all about these in this lecture. Actually, a unit cell is defined as the smallest unit of the lattice which on continuous repetition generates the complete lattice or complete crystal. Okay? So you can say that unit cell is actually a building block which when repeated in all directions that will build the whole crystal. Okay? As you know, whenever you construct, let us say a building, then you know the bricks act just like a unit cell because when you use the bricks in all directions, possibly all directions in accordance with the structure, the building is constructed. So you can say that this unit cell is just like a brick, or this plays just the role of a brick as the brick plays in case of a building. Okay, so we simply say that a unit cell is a building block, and due to its repetition in all direction in continuous manner, the whole crystal or whole lattice is constructed. Okay. Now, what should be actually the shape and size of this unit cell? This shape and size of the unit cell is actually arbitrary, but we always think about convenience. What will be the convenience way of selecting a unit cell? So you can say that there can be more than one choice of selecting a unit cell. For example, if you are talking about a plane lattice, that is the two-dimensional lattice, then the most convenient way of selecting a unit cell is a parallelogram. It means if you are talking about a plane lattice, then it will be more convenient to select the unit cell in the form of a parallelogram. Okay. Now, actually, in case of selecting the unit cells, both the primitive and non-primitive translation vectors may be used to construct this unit cell. And since both primitive and non-primitive translation vectors are used to construct a unit cell, so in accordance with this, you can say that a unit cell will be of two types. The first one is called primitive unit cell and the second one is called non-primitive. The name actually implies its meaning. When the unit cell will be constructed by using the primitive translation vectors, then that will be called a primitive unit cell. And if it is constructed by the use of non-primitive translation vectors, then it will be a non-primitive unit cell. But there may be a simplest way to differentiate between this primitive and non-primitive unit cell. If you consider that there is a unit cell and the lattice points are lying only at the corners of the unit cell, only at the corners, nowhere else, then such a unit cell is called primitive unit cell. So I have mentioned it here. You can see that in a primitive unit cell, the lattice points are only at the corners, nowhere else. Okay. But just in opposite manner, you can say in a non-primitive unit cell, lattice points are not only at the corners. It is these points are at the corners too, but apart from the corners, the lattice point will lie at another places, at another sites too. So you can say that in case of a primitive unit cell, the lattice points are only at the corners, but in case of non-primitive unit cell, lattice points are at corners and also at other points uh, which are not lying at the corners. I have shown in this figure two unit cells. Both are parallelogram, you can see. So these will be the unit cell of a plane lattice or two-dimensional lattice. Okay. See this first figure. I have shown in this first figure that this ABCD, which is a parallelogram, the lattice points are only at the four corners A, B, C and D. There is no lattice point except this corner points. So this ABCD in this figure will represent a primitive unit cell for the plane lattice. Okay. But in second figure you can see, apart from the lattice point at the four corners E, F, G and H, there is a lattice point also lying, let us say, at this point P, which is not at the corner of this parallelogram. So this EFGH parallelogram represents a unit cell which is not primitive. It is non-primitive. I have marked it here NP, which means non-primitive. So you can see I have mentioned it here that ABCD is a primitive unit cell of plane lattice, while this EFGH is a non-primitive unit cell of the plane lattice. I think you have clearly understand what is the basic difference between a primitive unit cell and a non-primitive unit cell. I am just repeating the fact. If the lattice points lie only at the corners of the unit cell, then you will call it primitive unit cell. While if the lattice points are lying not only at the corners, but apart from corners, lattice points are lying at another points too, then you should say that such a unit cell is a non-primitive unit cell. Okay. Now let us see this figure. I am marking here, this is figure 1 and this is figure 2. In figure 1, which represents a primitive unit cell, you can see that this primitive unit cell of plane lattice is characterized by two translation vectors. First one is A and the another is the translation vector B. And the angle between these two translation vectors A and B is phi. Actually, this primitive unit cell for the plane lattice is characterized by these three quantities, that is A, B and phi, in which A and B represent actually the translation vectors and phi is the angle between these translation vectors. Okay. Now you know there may be different values and different choices of these A and B, A, B and phi. So accordingly, when we will take the different choices for A, B and phi, we will get the different primitive unit cells for the plane lattice. So I have mentioned it here. You can say that depending upon A, B and phi, there may be many choices of unit cell for a plane lattice. Okay. So in nutshell, you can say that in case of plane lattice, it is convenient to take the unit cell in the form of a parallelogram, and this parallelogram is characterized by three quantities, in which two quantities are A and B, which are actually translation vectors, and or you can say primitive translation vectors, and one is the angle phi, which is the angle between A and B. and taking A, B and phi in different ways or different values, we will have more than one unit cells for a plane lattice. Okay. Now, after getting the idea of unit cell, the primitive unit cell and non-primitive unit cell, now we will see what should be the most convenient unit cell in case of a three-dimensional lattice, or you can say the space lattice. Actually, in case of a space lattice or three-dimensional lattice, it is most convenient to take the simplest parallelopiped as a unit cell. So in this case, instead of parallelogram, we should take a parallelopiped as a unit cell. As you can see in this figure, I have shown here a parallelopiped, and this X, Y, Z axis marked here actually represent the crystallographic axis. Okay, and this parallelopiped, in this parallelopipe there are 6 quantities, you can say. There are 3 primitive translation vectors A, B and C, and 3 interfacial angles. One is alpha, which is actually the angle between B and C. Another angle is beta, which is angle between A and C. And the third one is gamma, which is angle between A and B. Actually, this primitive cell is uniquely defined or characterized by these six quantities, among which there are 3 edges A, B and C, and 3 angles A, alpha, beta and gamma between these edges, as I have shown in this figure. Okay. Now, we will again talk about the primitive and non-primitive unit cell in this case. Okay. But before that, if the sides of this parallelopiped are represented by the vectors A, B and C, what will be the minimum volume of this unit cell? As you know from the geometrical interpretation of triple scalar product of vector, that the volume of this primitive unit cell will be given by modulus of A dot B cross C, or equivalently you can write it, this is equal to mod of B dot C cross A, and it may be also written as mod of C dot A cross B. This is actually the volume of this primitive unit cell, or you can say this is the minimum volume of this primitive unit cell. Okay. Now we will learn about the density of lattice points per unit cell. It means what will be the number of lattice points in a unit cell. In fact, in general, if you want to know what is the number of lattice points or number of atoms in a unit cell, you can use this formula. The total number of atoms or total number of lattice points in a unit cell, particularly you can say a cubic unit cell, or the unit cell in the form of a parallelopiped, this total number of lattice point in this unit cell is given by this formula. This n is equal to Ni plus Nf divided by 2 plus Nc divided by 8. Actually here this Ni represents the number of interior or body centered lattice points. It means Ni represents the number of lattice points in the interior of the unit cell. Okay. And Nf, this represents the number of lattice points in the face of the unit cell. And Nc represents the number of lattice points at the corners. Okay. Actually, these subscripts I, F and C have been used for the word interior, face and corners. Okay. Using this formula, you can easily find what will be the number of lattice points in a unit cell. So for example, first of all, let us consider the primitive unit cell. As you can see, if we are talking about a primitive unit cell, you know, in this case, the number of atoms will be only at the number of, in this case, the lattice points will be only at the corners, no other places elsewhere. So as in this case, in this parallel pipe, you can see there are 8 corners. So there will be 8 lattice points at the corners of this unit cell. Okay, but each lattice point is shared between the similar 8 unit cells. So in this way, you can say that each cell is shared between 8, each lattice point is shared between 8 cells. So only 1/8 part of the lattice point is inside a given unit cell. Okay, and so the total number of lattice point inside this in this unit cell will be only 1. But using this formula, this calculation will be very easier. As you can see, in case of primitive unit cell, there is no lattice point in the interior of the cell. So Ni will be 0 because Ni represents the number of lattice point in the interior. But here we are talking about primitive unit cell, and in case of primitive unit cell, there is no lattice point in the interior. Only the lattice points are at the corners. And similarly, there will be no lattice point at the face. So NF will be also 0. But since there are 8 corners and at each corner there is a lattice point, so number of lattice point at the corners, which I have represented by the symbol NC, that will be equal to 8. And that lattice point is shared among the 8 unit cells. So substituting these values in this formula, which I have mentioned in this equation 2, you can see that the total number of lattice points in this unit cell, which is n, will be equal to what? This will be 0 plus 0 by 2 plus 8 by 8. And so it is obvious this will be equal to 1. So you can say that the number of lattice points in a primitive unit cell in case of the space lattice is simply equal to 1. This is a most common or most important figure. You must remember it because it will be very important for your objective type of questions. Okay. Now we are talking about the non-primitive unit cell. You know, I have learned that in case of non-primitive unit cells, the lattice points will also lie at the other points apart from the corners. Actually, in case of cubic crystals, there are 2 important non-primitive unit cells. And those 2 important non-primitive unit cells are body-centered cubic cells and the face-centered cubic cells. In abbreviation, you can say BCC and FCC. Okay, BCC and FCC. Now we will see what will be the number of lattice points content in the BCC unit cell and the FCC unit cell. Okay, you can easily calculate it. Let us see this figure. I have shown in this figure a unit cell which is actually body-centered unit cell. You can see at the 8 corners there are lattice points as I have marked in this figure, you can see easily. And apart from that, there is a lattice point, let us say at this point P, which is actually at the center of this unit cell. So in this case, apart from the 8 lattice point at the corners, there is also a lattice point at the center of this unit cell. And this is in fact in the interior of this unit cell. So in this case, the number of lattice point in the interior Ni will be what? This will be equal to 1. Okay. But even in this case, there is no lattice point at the face. So NF in this case will be again 0. But since there are lattice point at each corners, so NC in this case is again equal to 8. Okay. So now we will substitute all these three values in this formula for getting the number of lattice points inside this unit cell. So N is equal to what? You know, this is Ni plus Nf over 2 plus Nc over 8. But Ni is 1, but Nf is 0. So this is 0. And Nc is 8. So this is 8 upon 8. So this will be simply N equal to 2. So you can say in case of a body-centered non-primitive unit cell, the number of lattice points in the cell is equal to 2. So the density of lattice points is just 2 times of the density of lattice points in case of simple cubic lattice, or you can say the primitive lattice cell. Okay. Now, see the case of face-centered cell. When you say face-centered cell, you know, in this case, there will be lattice point at 8 corners, it is at each. But apart from that, since this parallelopipe, you know, has 6 faces, there are 6 faces. You can see the one face is AHED, and at the center of this face AHED, there is a lattice point which I have marked by this point P1. Okay. The another face is CDEF, and at the center of this face there is a lattice point at point P2. Again, you can see there will be a lattice point at P3, at P4. Okay. And apart from that, the center of the face ABCD, see the figure ABCD, this is at, let us say, point P5, and here there is also a lattice point. Again, the sixth face is EFGH, whose center is at, let us say, P6, and there is a lattice point here too. So what you are seeing in this case? In this case, then there is no lattice point in the interior. So Ni is equal to 0. But there are 6 faces, and at the center of each face there is a lattice point. So the number of lattice point at the face, at the center of the face, is equal to 6. Okay. And at each 8 corner there is a lattice point, so NC is again 8. So now we will again substitute all these 3 values in this formula for getting the number of lattice point per unit cell, which is N equal to Ni plus Nf by 2 plus Nc by 8. But you have seen that Ni is 0 and Nf is 6. So this is 6 over 2 plus Nc is 8. So this is 8 over 8. And so this will be 3 plus 1, that is 4. So the number of lattice point in face-centered unit cell is equal to 4. So the face-centered unit cell is the most dense cell, most dense, and the primitive unit cell is the most rarer. Okay. So I think you have clearly understand what is a unit cell, how many types of unit cells are, how we select a unit cell, how they are characterized, and how we can find the number of lattice point in a unit cell. So this is all about the unit cell in this present lecture. Now we will learn about the some new concept in the forthcoming lecture, and I hope you will definitely enjoy all these lectures. Thank you very much.